Hi, this is Chris Overholt, and this module will go over the verification and validation of fire models as part of the 3D fire modeling course. In this module, I'd like to talk about the verification and validation of fire models in general, but also specific to Fire Dynamics Simulator, FDS, and what guides are available, the definition of verification and validation, and what that means for the model end users and the model developers. Now, verification and validation have become an important topic in fire modeling, and I'd like to distinguish between the two before we move on. So, verification is defined by ASTM E1355, which is a standard for determining the, let's see, I'll show it here. Here's standard guide for evaluating the predictive capability of deterministic fire models. And this applies to zone models, field models, all types of fire models, and this guide lays out the process of verification and validation for both of those. So with that, the definitions here, the verification is defined as the process of determining that the implementation of a calculation accurately represents the developer's conceptual description of the calculation method and also the solution to the calculation method. Essentially, verification answers the question of, is the math right? In other words, in the submodels in FDS, for instance, the radiation submodel or the pyrolysis submodel, is the math, or the way that the code is programmed, is the math correct, and does it match the developer's concept of what was supposed to happen? And we'll look at some examples of that later on. One example of verification from the FDS verification suite is called radiation inside of a box. And in this example, this is included with the FDS installation, and we'll actually look at this in a few minutes. What this does is set prescribed conditions on the walls, and it's a one-step calculation. And on the right side here, you can see various a line of devices going up and down the wall, and we have radiation coming from a hot wall going inside of a box. And what this case serves to do is to ensure that the radiation submodel is programmed correctly, and it's a simple case. One would think it's a trivial run, but it's very useful in seeing if one of the lines of code in FDS may have a problem. Another example shown here is a 2D solution to the Navier-Stokes equations. Here it shows a slice of the pressure. On the left side is a coarse grid, on the right side is a finer grid, and in this case we're looking for a convergent solution as you refine the grid. So these are both examples of checking the math of the model to make sure that it doesn't have any bugs in the actual code. Now on to validation. ASTM E1355 also defines validation, but it's defined differently in that it's defined as the process of determining the degree to which a calculation method is an accurate representation of the real world. That's the key part, from the perspective of the intended uses of the calculation method. So in essence, validation answers the questions, are the physics right, or can FDS or some other fire model do that? Such as, can FDS model sprinkler activation, or can FDS model flame heights accurately, and so on. And so validation cases are typically compared to real-world experiments that are instrumented well at a high enough resolution to where we can compare FDS to experiments such as temperatures, flame heights, heat fluxes, sprinkler activation times, and so on. So validation is different than verification in that it's not only a check of the math, but it's a check of the physics and how well they represent the real world. Some examples are given in the guide that we'll look at in a minute from the FDS validation guide, and from this there are numerous experiments that have been compared to FDS where the uh, experimental model was built in the FDS geometry, fire conditions, boundary conditions, and so on, and it was instrumented in a way that was similar to the experiment, so we can compare side by side the results. And shown here is a typical plot from the validation guide where we have hot gas layer temperatures from a specific test, and we have two different curves shown here. Typically the solid line is from the experiment and the dashed line is from FDS. On the right we have the hot gas layer height compared, and you see the general trends are followed by FDS. This is very useful for a couple of things. One thing it's useful for, the end users are able to see and quantify how well FDS performs for certain situations. Another thing that it's helpful for is for model developers. It's very useful for them to see where work needs to be done, and it quantifies real-world cases with FDS simulations. So very useful, and this is a typical set of plots from that validation guide, which are full of plots like this. In the end, it's up to the end user to decide for himself if he's using FDS in an appropriate manner for his solution. Here's another case of plot, another set of plots from the World Trade Center FDS simulations. This shows heat fluxes to the columns, and again the solid line here in the plots indicates the experimental data, and the dashed line indicates the FDS simulation results. There are many different validation suites, validation experiments in the validation guide, and they're continuously being added, and work on this is continuous because validation is essentially an ongoing project to compare FDS to real-world results. There's another example from UL and NFPA Research Foundation experiments where sprinkler activations were modeled. Here's a layout of the experimental setup where draft curtains were present, and sprinklers are shown here as the different dots, and FDS was modeled in the same way. And here are a couple of the plots from that part of the validation guide where the number of actuated sprinklers is shown over time. The solid line is the experimental data, and FDS is the dashed line here. So this compares sprinkler activation in FDS, and again it's important to note that these are provided as information to the end user, and ultimately it's in the hands of the user or designer to determine if FDS or any other fire model is adequate for the problem they are handling. So in summary, verification and validation. Verification checks the math of the model, that it's in alignment with the developer's conceptual vision of what it was supposed to be, using simple checks, energy balances, radiation calculations, heat transfer calculations, and so on. Validation, on the other hand, was shown as a comparison to real-world experimental data. Whatever that may be, this is helpful for seeing how well the model is approximating reality, how well it's performing for a given application. And finally, this affects the verification and validation affects end users, model developers, and researchers in different ways. For the end users, it lets them see where FDS is appropriate, if it's performing well in a certain area, and it lets them decide how to apply the model. For the developers, it tells them where they need to work on specifically, or what physics in the model need to be improved. And for researchers, the same, it directs them on current topics and research on the model. So here are some examples of areas that currently need more work, as indicated by the FDS roadmap and various research work going on. Liquid pool fires is one. The liquid pyrolysis model is sort of in its early stages and is sensitive to many parameters. The CO, or carbon monoxide production model, is certainly being worked on, and multiple mesh solutions, and this is a wide topic of research from anything from parallel processing to multi-core processing. These are some areas that are pointed out that need more verification and validation work. Finally, another topic is how to quantify model uncertainty. In other words, how do you decide that a model is appropriate? You may have two curves showing temperature from the experiment versus FDS, but how good is good enough? Is 10%, 20% error good and applicable to a life safety problem? And again, that's up to the end user, but that can be now quantified using these verification and validation guides. One sort of plot or conceptual visualization of this is the scatter plots that you'll see in the validation guide and in different articles about model uncertainty, fire model uncertainty, where on the x-axis you have the measured temperature and on the y-axis you have the predicted temperature from the model, and then you have this line going across where points that lie below this line are being underpredicted by the model, and points above this line are being overpredicted by the model. In the case of some items, in the case of temperatures for instance, an overprediction of the model would be a conservative guess. So it's typically preferable to be on this side of the line, although ideally we want to be right on that line. You also see other statistical measures shown here, standard deviations and means and errors shown there. And the last thing that I want to show here is the different guides that are available that come installed with FDS. There's the FDS User's Guide, which we've been looking through throughout the course. It talks about input files, some examples, and so on. But in addition to that, there is a FDS, verification guide here. So this is the FDS Technical Reference Guide, Volume 2 Verification. And what this is a collection of verification cases. We'll be looking at one of these, the radiation in a box, but it goes over what is verification, some past verification work that's been done, and then you'll see different sections here broken up into the flow solver, radiation, species, heat conduction, pyrolysis, and particles. And under each of these main topics are subtopics. So under the heat conduction topic, there's a simple heat conduction case, and this corresponds to an FDS file that you can actually run yourself, and it shows what the case is, and it shows some of the plots, lots of plots in these guides for that case. So this is the verification guide. Additionally, there's the Technical Reference Guide, Volume 3, the validation guide, and this is validation as we discussed, and it contains what is model validation, a survey of past validation work that has been performed, a description of all of the experiments that are contained in here, and all the experimental data sets. It talks about quantifying error, and then finally it's broken up into different various phenomena like hot gas layer temperature, fire plumes, sealing jets, gas velocity, gas species, compartment pressure, surface temperature, and heat flux. And under each of these main topics are subtopics that correspond to the various experimental sets. So for hot gas layer temperature from the World Trade Center test series, you'll see a number of plots showing the experimental data versus FDS for different experiments. So that gives an overview of the information that's available just with FDS, the user's guide, validation guide, and verification guide, and how they can serve to help end users use the model appropriately and model developers to improve upon the model.